rectangular region which extends from the xy plane up to some surface, giving us ultimately a typical three-dimensional region within our three-dimensional surface. If we then add the volumes of these regions from the y-axis up to our surface, we get the volume corresponding, the volume lying above this rectangular region in the xy plane. If we add the volumes of these regions as we go from the x-axis up to whatever our boundary is here, then we get the volume of the region lying above this strip. And if we then add those up over all of our x regions, our x intervals of our x partition, we get the total volume of the solid. The total volume of our three-dimensional region. That total volume can be represented by a sum. We'll sum from I equals 1 to n with respect to x, indicating the regions, subregions into which we've divided our x-axis, of the sum from j equals 1 to m of I, whereas we recall the index I of our x partition determines how far we can go in the y direction, and then we can sum from here up to here. We'll write that as a sum from k equals 1 to, let's call it p of ij, where how far we go here depends on the sample point here, which is xi star yi star in the xy plane. So this position determines how far up we can go. It determines what z interval we partition. So we partition the z interval and we add the delta z, delta y, delta x for every one of these, giving us the volume of a typical stack here. Sum that over the j's, extending the volume to that of this entire strip, all the volume between here and our surface, between the strip and the surface. And then we sum those with respect to our x partition. And we let this approach as delta x, delta y, and delta z go to 0. This then approaches a triple integral with respect to z, with respect to y, with respect to x. First integral being our z integral, so that's going to go from 0 to z of x, y. Our second integral, and we haven't given a symbol to that, but I think we can understand if we call this from 0 to y of x, and then from x equals 0 to whatever this is, let's say x equals 0 to a. Now, we're assuming just this region. We're making a couple of implicit assumptions that our surface is simple so that it doesn't double back on itself and we hit the surface at two different points above an xy point. We've also sort of implicitly assumed that we have a bounding curve here that's a simple function y of x. That is, that if we move across here from any x value, we only encounter this curve at one point. we can deal with a situation where we have multiple encounters with the surface, multiple encounters with the curve here, but for most of our applications that's not going to be particularly complex or difficult to deal with. Note that z of x, y is a function of two variables which can define a surface in 3 dimensions. Once we've integrated z and substituted whatever this limit is, z dependence will go away. Y of x, similarly, once we've integrated with respect to y, we're going to substitute a function of x, and we're only going to have x's in the integral when we evaluate the x integral. Naturally, we aren't confined to considerations of volume, but we can use this model to deal with the implications of any quantity that occupies volume. For example, if we have density function delta of x, y, z, if we multiply the density at the sample point by the volume, the mass of our IJK region, contribution to the total mass of whatever's occupying this region, is going to be just density at xi, yj, zk sample points times delta v. Delta v is just delta x, delta y, delta z. So that instead of summing delta z, delta y, delta x, or delta x, delta y, delta z in whatever order we do this, we would be summing delta of xi star, yi star, zk star density function at these sample points multiplied by the volumes, and it's not difficult to see that that would give us a triple integral with similar limits of this function. And that would be the mass. If we wanted to find the moment of inertia about the x-axis, well, our from here to here is just from the x-axis to the point xi star, yj star, zk star. We have to go over yj star up zk star units, so that our for the mr squared that we would add up to get the moment of inertia about that axis would be just yj star, square root of yj star plus zk star. And our mr squared would just be our density function times y star, yj star plus zk star, yj star squared plus zk star squared times delta v. So we would have ultimately in this integral, we'd also be multiplying then by y squared plus z squared. Once we understand how the partition of the x interval, the partition of the y strip, and the partition then of the z prism lead to the integral, it becomes easy by considering just whatever happens in this small volume increment to build the expression for the integral that we're looking for, giving us a very powerful tool for analyzing things that happen within three-dimensional regions. And the three-dimensional region doesn't necessarily have to be interpreted as a region of the three-dimensional space we live in. The x, the y, and the z could represent any quantities. This could represent one observed quantity in experiment, this another observed quantity, this a third observed quantity. We can integrate vectors through volume regions, And we're going to see a lot of that.